So in this week, we'll be providing some tutorials to help you understand what we have been covering. Not only that, but more about preparing you for uh, homework 1 and homework 2 and homework 3. So it's not really about homework 1 because homework 1 is way too easy. You probably don't need this tutorial to complete homework 1, but reading these tutorials will kind of make your code a little bit more elegant and shorter and more powerful. Um, Not just for week for homework 1, but also for homework 2 and homework 3. So you'll be writing more and more idiomatic code using better and better features of NumPy. So this tutorial is a kind of fused tutorial of many different tutorials. So it has a linear algebra review, geometric intuitions behind linear algebra, and also a NumPy tutorial, and also a matplotlib tutorial, which is part of NumPy. So it's kind of 4 tutorials in one. So it's the best I can do. So I'll try to kind of cover these 4 very different topics in just a unified unified kind of framework. So to do that, I'll use Jupyter Notebook or IPython Notebook, which most of you have been familiar with. And let's start a new one in Python 2 for now. And I'll save and upload this notebook so that everybody can play around with it. But for now, let's import NumPy as MP as a shorthand. And the first thing we'll do is just create kind of a vector, and this vector is a 3-dimensional vector. So if we say x is that, and what is the shape of x? The shape of x is nothing. It's a tuple that is just 1-dimensional 3, because what is x? X is this, and what's the type of x? It's ND array, which means n-dimensional array. Now here, the n-dimensional array, this dimensionality is very different from the dimensionality of the vector that we were talking about. For example, if you look at x, x is definitely a 3-dimensional vector. So it's basically some point in the 3-dimensional space. You can understand it that way. But in terms of array, it's a 1-dimensional array, right? And for those of you who have done a lot of programming, you understand that there are 2-dimensional arrays, like a square, like a table, 2D table, and 3-dimensional arrays, like a cube, and 4-dimensional and higher dimensional arrays as well. So the ND array in NumPy, this n is not about the length of or the vector, and here this length of the vector is 3, but it's still a 1-dimensional array. It's a 1-dimensional array but 3-dimensional vector. Okay. So what if we have a 2-dimensional array? So for example, say np.array, 1, 2, 4, 5. So this is a 2-dimensional array, or a matrix in linear algebra's terminology. And the shape of that, so let's call it y, or call it a. We use uppercase for matrices. Okay, a dot shape is 2, 2. Okay, and a is also an ND array, right? But in this case, it's 2-dimensional array. Now, don't worry about these things for now, and I'll introduce this concept called a range. So a range is just like Python range. So if you remember Python range, it's a range of 10, just 0 to 9. And a lot of things in Python will be kind of numpized. In other words, there are NumPy correspondents or equivalents which will return ND arrays. So if you say np.range, well, np is called a range, and it will return very similar stuff. So what's the difference between a list of 10 numbers and an array of 10 numbers? Well, a list of 10 numbers is a Python object or Python data structure, but array of this vector of 10-dimensional vector is an ND array, is a NumPy object, and you can apply NumPy operations like plus, minus, these stuff very easily on that. and you can do dot product, you can do take the norm or whatever. So that's the difference between range and arrange. Okay, so let's see. For example, if you say x is this NP.range, now what is x? X is that. What about if you say x plus x? Well, if you remember that if you say range plus range, so let's say if there's y is range of 10, okay. Now y plus y, what is that? That's basically concatenate y at the end of y. So y becomes, you know, a 20-dimensional last 20 list, okay? But what is x plus x? Is that the same thing? Concatenating two vectors? Well, actually no, it's element-wise addition. So that's very different from Python concatenation. The plus in Python, when facing two lists, are interpreted or actually overloaded to be concatenations between two lists. Now, in NumPy, this concatenation, this plus is not concatenation, it's actually element-wise addition. So each element, for example, you know, the first dimension is 0, the second dimension is 1 plus 1 becomes 2, you know, third dimension 2 plus 2 becomes 3. So this is as if you just do a scalar product, like x times 2. Exactly the same, okay? Whereas in Python, you say, well, it's still also the same, like if you say y times 2, it's basically the same as y plus y, but just because, you know, these plus are interpreted differently, okay? All right, but how do you want to do concatenation in NumPy? Well, there's still a way to do it. You say numpy.concatenate x, you have to supply that kind of a pair, a tuple, and that gives you this concatenated version, concatenated elongated 20-dimensional vector. Okay, so that's that, and yeah, and now we also wanted to demonstrate the norm, right? The norm of a vector. So for that, you need something called np.linear algebra. So np.linalg, it's linear algebra.norm. So that takes the norm, the L2 norm, okay? And it's basically like the square root of the sum of squares of each dimension. So in other words, you can, so if x is that, you can just say for a times a for a in x, that's basically the squares of each dimension, and then you sum it. You sum that list, and that gives you that. Well, what's the difference between here and that? Well, because the sum, you have to take square roots of it. Square roots of the sum. Oh, because square root is not imported, so you have to import that from, so you say from math import star, you know, this is just being lazy, so that it imports everything like ABS, square root, log, or whatever. But that's exactly the same as what we computed from np.linag.norm, right? So exactly 16.88. That's the norm of that vector, right? Okay, in 10-dimensional space. So yeah, to make a simpler example, so if you say, I'll say np.linag, linear algebra, linalg dot norm, well, np.array. What about if you just have a 1, 2 vector? That's 2 point. So you can easily verify that. So 1 plus 1, sorry, 1 times 1 plus 2 times 2. That should be the same. Yeah. So that's the L2 norm. That's the length of the vector that we used a lot in these 3 weeks. Okay, so what else we need to cover? Well, what about the dot product? So the dot product is also very interesting. So if we have, you know, two vectors, A, which is np.array 1, 2, and B is np.array, let's say 3, 1. What's their dot product? Is it just A times B? No, because A times B, remember that A plus B is element-wise addition, so 4 for the first dimension and 3 for the second dimension. Similarly, 8 times B is element-wise multiplication as well. So you can imagine the result being 3, 2, right? First dimension 1 times 3, second dimension 2 times 1. So this is not what we wanted. What we wanted is a dot product, which returns not a vector but a scalar. So A dot B instead. It's 5. So basically 1 times 3, 3 plus 2 times 1, 2, so it's 3. This is 5, sorry. And you can verify it by writing Python this comprehension. So it's basically like, x times y for xy in zip of AB. Well, so this is basically doing the zipping of AB, and this is 5. Right, so this is the list comprehension way of verifying the dot product. So for those of you who are not familiar with zip, well, you can just verify that and just say, well, what about xy for xy in zip of, well, first of all, what is zip of AB? Well, zip is a Python function, not a NumPy one. Zip of AB returns that. So, but normally speaking, this should be Python lists instead of NumPy lists, but it can be converted very easily to Python lists. So zip of AB takes 1 3 pair and 2 1 pair. So basically like the pairs, and then xy in this. So xy initially is 1 3, and then it's 2 1. So if you just want to say xy for xy in zip of AB, well, that's boring because it's just returning the same thing. And now you replace this by times, and becomes 3 2. So this 1 times 3 and 2 times 1, and then you sum them up. Okay, that's fine. So that's the dot product. Very easy. And we'll talk about the geometric meaning of dot product slightly later. But let's do some fun experiments first. So remember, we have covered linear regression in week 1 as a very simple kind of example of machine learning. Now let's try to do that in NumPy. It's very, very easy to do. And I'll do it in the next short video.